Good afternoon. My name is Hayden McAlpin, and I did my project over a classification of pump functionality by using the Naive Bayes Classifier. And so just kind of to go over what we'll go over in this presentation today, we'll look at an introduction, kind of defining our problem, looking into that, some related work, how the Naive Bayes Classifier has worked in the past, and the objectives of the project. Then we'll kind of dive into the data, get an explanation of what the Naive Bayes Classifier is and kind of how it works, how I was able to implement this model in my program, look at how I evaluated the model, look at some results, and then also get into the graphical user interface that I created. And then, of course, go to our conclusions and look at some continuation work that is possible, as well as do a short little demo on how the graphical user interface works. So, kind of getting into the project, as we know, water is an essential resource for human life, right? And it's important that the water that people consume is safe and clean, as unclean water can hold contaminants that are harmful to the human body. Contaminants in groundwater may include natural substances like arsenic or other things that from the soil that are harmful for the body. There's also things like runoff from agricultural activities, discharge from sewage treatment, and even leakage from landfills. And so these things can cause serious issues in the water, sanitation, and things like that of certain areas. And while clean water is pretty common here in the United States, um, it is an important problem in many third world countries, including um, and in other countries, not just third world, but other developing countries. But Tanzania is going through a water and sanitation crisis as millions of people across the country, and this is located in East Africa, they don't have access to a safe source of water, and even more don't have access to healthy sanitation sources. So, what they do have are various water pumps that have been placed throughout the country, and their functionality is important as these are some of the limited sources of water that the population of Tanzania can go to. And so, keeping track of how functional they are, whether they're still working properly, need some repair, or are no longer functional, it is important to know that ahead of time so that it is easier to keep the water safe for consumption of the Tanzanian population. So, to attack this problem, drivendata.org created a competition, and they have various other competitions, kind of like Kaggle does or KD Nuggets. Um, some of the so it's actually pretty good. Um, so for this, it supplies a set of data that we will get into later, and just asks you to build a model that can accurately predict um, the functionality status of the water pumps given in the test data. And I decided to use the Naive Bayes classifier as it is easy to implement into classification problems, and there is an extensive amount of research in previous projects done using this model. So kind of getting into some of the things that the Naive Bayes classifier has been used for. It is used for text classification, um, sentiment analysis, and in this study, it had three different class variables, which is similar to that of how this project is. And it was also used in a study on heart disease detection. And so, as I mentioned, this classifier is commonly used, and it can even compete with some of the other more well-known classifying algorithms. And as classification is a important tool in the data mining realm of data science, um, it was suitable to use for this project and towards this problem. So kind of going over the objectives of this project, we were looking to explore how the naive Bayes classifier works and um, kind of get into its details, and then develop predictions for the water pump functionality over areas of Tanzania, as well as create a graphical user interface for users to use and see the results of the model. So looking at the data, the drivendata.org acquired the data from the Tarifa database, which holds all sorts of different infrastructure data for various regions of Africa. And specifically for this project, they took in data for the water pumps. And the trained data file had 40 different variables. And to save time, I'm not going to list all 40 out for you, but um, there are a lot of repetitive variables as well. There's a lot of like locations, breaking it down by different parts of the country, as well as the source type, extraction type, and there's just various variables that kind of link together. The train labels is just a data file that is filled with the ID of each pump and the functionality status of said pump. The test data has all the same variables as the train data, but it just doesn't have any of the labels, obviously, because that is what we're going to be predicting. So in order to prepare the data for our modeling, I first had to merge the test file and the test labels file. I was able to do this in R. So if I had mentioned earlier, all of my coding, all of my calculations and modeling was done in the R software using the RStudio IDE. And in R, it has a function merge, and I was able to merge these two data frames once they were read into the file by their linked IDs. And so once I had this file, I checked for any missing values, and it turns out there were quite a few, but it wasn't a very large proportion of the data. So removing those instances didn't really hurt our modeling process, as having missing values can cause errors and inconsistencies in the model, but removing these created opportunity for more accurate results. And as I mentioned earlier, there were a lot of attributes that were kind of linked together. So I went ahead and chose 8 of the attributes to use. The ID and longitude and latitude were not used in the modeling process, but they were used to identify the separate pumps and also graphing the pumps in our exploration and result stage. But the attributes I did select were the TSH amount, the basin, which is just the location across the country, the population, the construction year of the pump, the extraction type, the water quality that the water pump resulted in, the source type, which is just where the water is flowing from, and then the water point type group, which is just kind of the type of water water point that the citizens can get the water from. So kind of looking at some of our different attributes, was able to graph the different basins and kind of where majority of pumps are located, and also color the bars by their functionality status. So as you can see, a majority of the pumps are located in the Lake Victoria and Pangani in the Rufiji basins, and then the least of them were located near Lake Rukwa. Then it looks like a lot of them are functional. So here is our water quality, and so a vast majority of the pumps have a soft water quality, and very few had fluoride abandoned. Really, any of them had very low counts in comparison to soft, so this can cause some distribution issues in our probabilities. That is okay, because this classifier is good at handling things like this. And this is kind of the distribution of the years in which these pumps were constructed. A lot of them were constructed after the year 2000, but some date even back to prior to 1960. And there are actually pumps functional in all years that these were constructed. So here's kind of the spread on the pumps and where they are located across Tanzania. These are the longitude and latitudinal coordinates of the pumps. And you can kind of see where they're all located relative to each other. And there's quite a big spread on what's functional, what's not functional. Right in here, you can kind of see that a lot of our data is functional, which is awesome. And then kind of this southeast corner has a lot more non-functional in comparison to the rest. So getting into the naive Bayes classifier, this gets its functionality from the Bayes theorem. How the Bayes theorem works is that the probability that something happens given some information is equal to the probability that the information given that what we want to happen happens times the probability of what we want to happen happens at all divided by the probability of the data that we get. So for the naive Bayes classifier, we actually don't need to calculate this predictor because we are assuming independence amongst the variables. And then for the rest of the project, I'll be referring to these different probabilities as the posterior, which is the class label, the probability of the class label given the data that we are given, and the likelihood, which is the probability of the data given the class label, and the prior, which is the probability of the different class labels. So in the context of this problem, C will be our functionality class. So just the different levels. So they can be functional needs repair, or non-functional. And then X will be the pump data of the various attributes that is given. So first, in order to use our formula, we need to calculate the priors. And in order to do this, R has a function prop.table, which provides the probability distribution of the file given. And so here I was able to do the probability of train of the status group. And so as we can see, a majority of them are functional. Some little need functional needs repair, and then a large chunk are also not functional. Then we would need to find the likelihood of our variables. And to do this, for the numerical datas, the amount, TSH, and the population, we would use this formula right here. And this uses the normal distribution. And so this is the equation right in here for that. And it converts our numerical values to a normal distribution and then finds the probability of the value given. For our categorical data, I used the same process as to find the priors. And so given the test data, I was able to split it up for water point, basin, source, extraction type, year, all of those variables. And so they are all made in a similar fashion to this. And it returns the population of the given data value. And in order to use these functions, I first had to separate the trained data into 3 different categories. First was the all functional pumps in the train dataset, the functional needs repair dataset, and then the non-functional dataset. And so these probabilities are calculated within each dataset and then combined in the end. So once I have the likelihood and prior values, I stored them in their own data frames and then multiplied all these values together, as that is what is used for in the classifying algorithm. So now to evaluate this model and to determine the correct combination or the best combination of attributes to use in our model, I use the F1 score. And the F1 score is a little different than just accuracy. As with accuracy, if say your trained data has a vast majority of say non-functional pumps, right? Your algorithm could easily just say, oh, I'm just going to make them all non-functional and I'll still get majority of them right? What this actually takes into account is whenever you do make correct predictions, but also takes into account when your corrections are wrong. And so this is a better evaluation than just straight up accuracy. And so kind of going through and choosing the best combination of attributes, I started with all 8 of these selected, got the F1 score, and then went and removed each attribute one by one and saw which one had the most improvement. Here, given in the table, at each stage, I just put in the top 2 F1 scores. And so here, there was some improvement. Most of it was made when I removed no water point. So from there on out, I would not use the water point attribute. And then moving forward, I removed all of the other attributes along with water point. And the top 2 improvements were with extraction and year. But year had a better F1 score. So I then removed year from the attributes. And then moving forward, kept doing this process until I removed water point, year, and quality and got the F1 score of 0.4998. And then after that, I removed every other attribute one at a time to see if there was any improvement, and no improvements were made. So this turns out to be the optimal combination of attributes for our model. Okay, so now when used, I was able to then use this model on the test data. And this is the predictions that it gave. So it's saying that a lot of the pumps are no longer functional. And going back, as you can see, these F1 scores are not optimal. The closer to 1 that we could get would be perfect, but that's okay. The goal of this project was just kind of exploring how Naive Bayes Classifier works and how it can be used for a classification problem. And so just highlighting those points was good. Going back, this is kind of the predictions made. These regions are pretty similar. This south region of the center is functional, is majorly classified functional as it was in the test data, or in the train data, and the southeast corner is also majority non-functional, which is also the same. And then we can kind of separate and look at each basin and see how these work. And so in the Lake Rukwa Basin, most of them are non-functional, but there are some areas that have some functional water pumps. So, and then the Lake Nyasa Basin is kind of the opposite. This is in that south central area of Tanzania, as most of them are functional. So say you're trying to decide between whether you want to go visit the Lake Nyasa or Lake Rukwa, even though our model is not the best, it still gives a pretty good idea that we would rather go see Lake Rukwa instead of Lake Nyasa. And so we could go in and kind of focus on fixing and working on those pumps instead of Lake Nyasa. And here, Lake Tanganyika and Lake Victoria, you can kind of see that most of them are non-functional. If we had to focus on different areas within these basins, we'd want to focus on the ones that had most red to go in and fix and work on those first, as there are some functional water pumps in these areas. Pangani and Rufiji all have good mix, and so between all of these, it would probably be most important to focus on these two basins. But yeah. And also these ones as well. These are a little more scattered, like so the Wami Ruva basin is a little more scattered, so it would probably be best to look at this one, as there are more non-functional pumps kind of clustered together. So it would be easier to kind of work on these pumps in a given time to kind of save time with travel and things like that. So now the graphical user interface I developed was also in R using the Shiny library package. So what this does is it allows the user to select which area of Tanzania it would like to view. It has the choice of the whole country or the different basins. And then you can also highlight over given coordinates or given pumps, and it displays the coordinates and functionality status in a table for you. And I'll go over a demo of that here shortly. But in conclusion, the classifier was successfully implemented, which is awesome. The model gave decent predictions, not great, but not the absolute worst. And our results do show various areas across Tanzania and their associated pump functionality that give users the chance to see which areas of Tanzania they need to focus on working and rebuilding the different pumps. Some future work to build on top of this project is going through and exploring every possible combination of the 40 attributes, which would take time, but with this model already developed, it's a little bit easier now to go through and view these combinations. Possibly using the Bayes classifier instead of the Naive Bayes, as the Bayes classifier does not assume independence of the attributes, and so this could lead to different results. And also looking at other classification algorithms and see if they work more optimally with this project or with this data set. So now I will kind of go through and go over a demo of my GUI. So this is my R code over here. Once it's all ran and all of the data model has been used and results created, you just run this Shiny app code and it will pull up our GUI. And so it gives the user a chance to select whichever region they would like to view. So let's say we want to go to the Pangani Basin. And then let's highlight over a specific area that we would like to look at. And so clicking and dragging over this area, we can look at various coordinates that we might want to go visit and their associated functionality status. So this is good. Really gives us an idea of kind of how everything looks and what we need to focus on. And once you have this area, say you just wanted just this size of an area to focus on, you can drag this around and it will give you the table of the data in this window, which is an awesome little tool to use. Going back, we can look at all of Tanzania and highlight over the various areas, just like that. And that is my project. So thank you. Thank you for listening, and I hope you're able to learn something from this presentation.